Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Jason Wright, who's a professor of astronomy and astrophysics at Penn State University. He's a member of the Center for Exoplanets and Habitable Worlds and director of the Penn State Extraterrestrial Intelligence Center. He works on a variety of problems related to stars, their planets, and life in the universe. His work in SETI, Search for Extraterrestrial Intelligence, includes searches for signs of extraterrestrial industry via waste heat, sometimes called Dyson Spheres. He is also a member of the Habitable Zone Planet Finder team. Welcome, Jason.
Thanks for having me.
Sure, yes. I want to start with one of your recent papers entitled Galactic Settlement and the Fermi Paradox, in which you say we have modeled the settlement of the galaxy by spacefaring civilizations in order to address issues related to the Fermi Paradox. And you say you included the effects of finite settlement lifetime, finite probe range, very long travel times, resettlement, stellar motions, and systems which are unsettleable. The Fermi Paradox is this contradiction or apparent contradiction between the lack of evidence of extraterrestrial civilizations and various high estimates for their probability, right? So apparently Enrico Fermi once asked, where is everybody, right? So the estimates we have in terms of just the size of the universe and the fact that we have at least one instance of life here on Earth, the probability of life being widespread in the universe is apparently quite high, but we don't find anybody, right? So you want to talk a bit about that?
Yeah, sure. This was a fun project that I did with Caleb Scharf, Adam Frank, and led by Jonathan Carroll Nellenbach. Yeah. The idea was to try and put on a firmer footing the idea behind the so-called Fermi Paradox. As you say, Enrico Fermi, the Nobel Prize-winning physicist, supposedly asked at a lunch, where is everybody? Having calculated in his mind that if there were spacefaring species out there, that they should be here by now. And his reasoning was, just as you said, that even if their ships don't have warp drive, even if they just have rockets like we do, the time it would take to visit all the nearby stars and then build some more rockets and continue to explore until you'd reached every corner of the galaxy is much less than the age of the galaxy. And so similarly to how the time it takes, say, people to walk around the planet is much less than the age of the planet, that means that basically we visited every corner of the Earth by now. So why aren't they here, goes the Fermi Paradox. And there are a lot of answers. A lot of people have suggested various reasons why they might exist and yet not have visited yet. Right. But the essence of it does come down to this argument that if you start launching ships, and those ships have settlements that launch more ships, that eventually you'd get to all of the stars in the galaxy. And to really do that properly, you need to think about a few things that hadn't been considered in the literature before. One of them is that stars move. So the galaxy is not just this grid of stars. It's not like you can have a map of the galaxy that's good for very long, because the stars are all orbiting the galaxy. And they also have a lot of random motion. When you talk about a gas of stars, like the stars are gas particles moving about in the galaxy. And so what that means is that if you do have a species that's spreading to nearby stars, and if those settlements are long-lived, they'll eventually get mixed up as the galaxy swirls around and the galaxies all move over. And so that had not been thoroughly addressed in the literature before. We were also curious how this idea that you'd fill the whole galaxy depended on things like, how often does a settlement ship launch from one star to another somewhere in the galaxy? Or, what if settlements just don't last very long? What if they last for only, say, 10,000 years? And then they're not there anymore. Well,
just because of self-destruction.
Or whatever. I mean, there's no reason to think that they'll always want to launch such ships, or that they will last forever, or maybe they'll just evolve into some other species that doesn't do that sort of thing. I mean, these are very long timescales that we're talking about. And so we put all of those things into the model, and what Jonathan was able to do was build a numerical model for a region of the galaxy, and just see what would happen if the ships are very slow, or they don't go very far, or the settlements don't last very long. Or we also included the possibility that a lot of stars are just unsettleable. There's just nowhere to settle. You wouldn't want to settle there for some reason, because we don't know any of these things. And so we wanted to know how the conclusion, that comes from the fact that they're not here right now, depends on those sorts of assumptions. And we found that it does depend on those assumptions. If things don't launch very often, if settlements don't last very long, if lots of stars are unsettleable, then you can get these situations where not a lot of stars in the galaxy end up being settled. And in particular, we wanted to check whether the solar system would have been settled at some point in the last 10 million years. And not ever. We said at some point in the last 10 million years, because we've had this parameter that sometimes settlements don't last. And if there had been a settlement on Earth, say, 1 billion years ago, we wouldn't know it. And so we can't say there's never been a settlement on Earth. We don't know that. And so we just ask what parameters are consistent with us not having had a settlement on Earth in the last 10 million years. And
yeah, so two things. One is, so the literature generally, as you say, talks about the sheer size of the universe, and hence they should be everywhere. But you say when you put in these assumptions, more refined assumptions and constraints, the answer is not that obvious. There is also sort of some critical initial conditions, right? So, we have to have a system that is stable. Earth has been around for 4.5 billion years, and we have evidence of intelligence life only in the last million years at the most. And so it took a long time for life to start and evolve. So initial conditions also matter quite a bit, right?
Well, actually, not, because Enrico Fermi's argument was, or at least what it seems to have been, this argument was actually put forth in the 1970s most forcefully, and then later attributed to Fermi. But the argument is that it only takes one really expansive species that sets up a bunch of these settlements, and they by themselves will take over the galaxy. And so it does require initial conditions, but the reason it feels like a paradox is that there are so many stars in the galaxy, and they've been around for so long. It feels like if even one of them started expanding, they would have taken over the whole galaxy by now.
Okay. And so the other assumption, I think you touched on this also, is that we seem to have a general assumption that every life would want to explore and go out and conquer. In other words,
Yeah.
The utility that we assign to humans is, we believe, is universal. It's quite possible highly evolved systems don't want to do that at all, right? So you assign some probability that might be the case as well in the model.
Well, actually, the model, like I said, it only requires one. And so the way that we parameterize that is how often a settlement would launch a ship that would go and create another settlement. How often do settlements reproduce themselves? And the motives for that, whether it's some sort of imperialistic conquest or simple curiosity, don't really matter to the model. The question is just, does it happen? And so what we find is that as long as they're sending ships out longer than they last, like more often than they die off. So if a settlement, say, launches a ship every million years, then as long as the settlements last more than a few million years, then you'll get this ever increasing number of settlements in the galaxy. And that kind of makes sense. If they only last 100,000 years and only launch ships every million years, well, they're not going to launch a ship.
Right.
But if they last long enough to launch 10, then they'll get a lot. So this doesn't have to be this let's launch as many ships as we can, let's spread throughout the galaxy. It could be a once every million years kind of thing. This fluke, they get some, Elon Musk equivalent that decides he's going to spend enormous amounts of money on these big vanity endeavors in space. And as long as it happens occasionally, it should propagate.
Okay, so we just need one. We just need them to send out a few ships, and it sort of exponentially grows. That is the idea, right?
Yeah, that's right.
So once you settle somewhere, that civilization takes off from there, and so again back to the question of, it took us close to 4.5 billion years to get to where we are, and many could argue we are not intelligent yet. And so is it possible? So if you look at just the Milky Way and the systems in it, I don't know if you have an estimate of this. How many of those? What percentage of those systems are sort of solar system like?
This is one of the things that's really revolutionized the field, is the appreciation that most stars have planets. And 25 years ago, we didn't know that. We didn't know if planets were extremely rare. But we've now understand, thanks to the exoplanet revolution and projects like the Kepler Space Telescope, that most stars have planets. And indeed, most stars have rocky planets. And some of those, at least, are the sorts of places we would expect to look for surface life in the habitable zones of their stars where there might be liquid surface water. So I think that answers your question.
Yeah. So do we have an estimate, Jason, of what percentage of the? It's probably tough to estimate, our solar system or habitable sort of systems in just the Milky Way.
Oh, so the total number, the Milky Way contains a couple 100 billion stars, and we might expect. The guesses, typical best numbers, are something like a quarter of them are going to have a planet like Earth, in the sense that it's rocky and kind of a temperate temperature. But that doesn't mean that it necessarily has water on its surface, or that it's inhabited. So best guess is something like a quarter of them, I would say. But it could be much higher, it could be a little less, but it's not 1 in a million stars.
So it's a very large number. Right. So that still, sort of. So what are your conclusions? So the typical literature conclusion is that it's really a paradox. We don't know why we don't see them quite often. So what are your conclusions from the paper?
Yeah, well, I would say that there is no Fermi paradox, frankly. The paper does support the general mathematical model that once you start one of these settlement fronts, off they go. But it parameterizes it. It could be that spaceflight is very hard and it just very rarely happens. It could be that, in fact, they have been here, just not in the last 10 million years, so we wouldn't know. Of course, it could be that they aren't out there. So there's a lot of ways out of the Fermi paradox. And in particular, what this paper shows is that the universe, this galaxy could actually be endemic with settlements all over the place. But unless they're very, very long-lived, we wouldn't necessarily expect to see one here. So an analogy that Caleb Scharf came up with was looking at the settlement of the islands in the Pacific Ocean. The islands in the Pacific Ocean have been visited by humans for thousands of years. But many of them don't seem to show any evidence of human occupation, or you'd really have to dig to find that humans were once there, or know the stories that they once had visited. So you do the math, and you can crisscross the Pacific Ocean many times in one lifetime, and humans have been doing that for thousands of years. And so you could sort of have a Fermi paradox for the Pacific Ocean. You see some atoll there are no people on it, they've had more than enough time to get here, where is everybody? And the answer is, for a lot of reasons, they just didn't come and stay here.
Yeah, so it doesn't necessarily have to be self-destruction. I mean, just looking at Earth, for example, it's sitting in a very precarious position that could hit by asteroids and could wipe out a civilization fairly quickly, unless it reaches a technological sophistication to get over it, right? So then in that case, Jason, essentially the lifespan that you can expect for a civilization is small. Is that one conclusion?
I mean, it's possible that they are typically short-lived. That is one way out of the paradox. But I mean, there are other ones. We look at this idea that some stars are just unsettleable, that you wouldn't settle there. I mean, perhaps every time one of these probes has come along to the solar system, they've seen that Earth is already inhabited and said, oh, well, that one's already taken. I guess we shouldn't set anything up here. That would be a perfectly good way out of the Fermi paradox, for instance.
So they might have had a flyover and we wouldn't know.
Well, right. I mean, if they haven't visited in the last, couple hundred years, there's no way we would know.
Right. Okay. Is it, again, from a parameterization perspective of the model, so if you take all the settleable stars and you get an average distance from system to system, if that distance is, let's say, x, and it's, because of the unsettleable stars, it's 2x, then the technology that you need to surpass that also sort of exponentially grows, right? As opposed to what I'm saying is that if it is x, you have some probability, but if it's 2x, that probability declines quite rapidly.
Right. The hard part, it would seem, of settling another system is the tremendous amount of time it takes to get there. It's hard to understand how to accelerate a lot of mass to anything near the speed of light, which means the typical time to get to the next star is hundreds of thousands of years. And, we have no idea how to build machines that could last that long or sustain life that long. So you're right. If many stars are unsettleable, then the nearest settleable one is farther away. And so now you're talking about, twice as long that you have to survive that journey. But do remember that the stars move. So another way of putting it is not that you have to last in space that long, simply that a good star coming close enough to hop over to in what maybe is only a 50,000 year journey, that doesn't happen as often. It happens more rarely, every few million years instead of every million years or something like that. So it just makes everything a little harder.
Right. Okay. And so generally speaking, there are so many uncertainties, so many different things that could go wrong, so to speak, coupled with the idea that very highly evolved civilizations may not want to do this at all. You're saying there is really no Fermi paradox per se.
There are just so many reasons you can imagine why we might not be visited. So many scenarios where there is a lot of life in the galaxy, just not here, other than us, I mean.
Right.
It's not really a paradox. It's a really interesting thought experiment, though, that has spurred a lot of people to think about the problem, which is great.
Right. Okay. So I want to jump into another paper this is about SETI in general, search for extraterrestrial intelligence. You say in SETI, when searching for beacons, transmissions intended for us and meant to get our attention, one must guess the appropriate frequency to search by considering what frequencies would be universally obvious to other species. So this is, we are now assuming there could be civilizations out there, and they may want to communicate with us, and that's a big if. And if that is so, you are suggesting here that so far, I guess, correct me if I'm wrong, Jason, so far the attempts that we have made is sort of just looking out and looking for anything. And what you are talking about in this paper is perhaps we can focus our attention to certain frequencies, perhaps, to get a higher probability of finding them.
Right, and this is an old problem. When we're looking for life elsewhere in the universe, one thing we might look for is someone trying to get our attention. One reason to do that, look for that, is that if it's out there, it'll be a lot more obvious than someone not trying to get your attention. Another is, that's the main reason, because it's going to be more obvious. And so it's the natural first thing that you would go look for, someone trying to get your attention. But then how are they going to get your attention becomes the question. And at that point, unfortunately, you have to sort of get into the minds of the aliens and say, what would they do to get our attention? What would be obvious to us? Another reason that you needed to make this assumption is back in the early days of radio SETI, they had to decide what frequencies they were going to observe at. So if there were radio waves coming from another star, it might be up at 100 gigahertz, or it might be down below 1 gigahertz, and you don't know what frequency to tune into. And so by saying, well, what frequency would they use if they were trying to get our attention? That helps you try to choose which ones to focus your search on, because you had to pick something. Now, today, we can actually scan billions of channels at once across the radio spectrum. And so it's much less important today for us to guess at what frequencies they might be transmitting at. It's also less important for us to presume that they're trying to get our attention. But that was something that needed to be done back in the 70s, for instance, when Frank Drake ran Project Ozma, the first radio SETI program.
Yeah.
So that's an interesting problem. How do you find someone who's maybe is also looking for you when you can't communicate with them? You have to guess what they would guess that you would guess that they would do. And you get into this recursion. Right. And so it seems impossible. But it turns out it's not impossible. There are ways to solve this problem. And so this was a problem in game theory that was proposed and sort of solved by Thomas Schelling, who was a Nobel Prize-winning economist. And the version of the game that he proposed was to look for someone who's also looking for you in New York City. And how do you find them if you can't communicate? You don't have a plan. You just have to guess where they're going to be looking for you. And it seems hopeless, but his point was that there are clearly bad strategies, right? You don't want to go to a random spot and just wait, because if they do the same thing, you'll never find each other. So that's clearly worse than just wandering around randomly. Wandering randomly will take a long time. You might never succeed, but it could work. But much better is to say, all right, well, if I had to meet someone and they're going to guess where to meet me, where would they guess? They would not pick a random location. They would pick a location that has some sort of salience. And so he would poll his students when he taught this concept and say, where would you, look for the other person, and when would you go there? Where and when? Those are the things you have to decide. And they very commonly came to similar conclusions, like I would meet them at noon because noon feels like a salient time, and I would meet them at, and then they would pick some famous landmark. And interestingly, this game was actually played on American television on a primetime news special where they took a bunch of people and told them to go find each other in Manhattan. And the people had to play this game. And so half of them said, well, Times Square, that's an obvious place to go. And so they went there. Some of them tried to find each other at Grand Central, and a bunch of them found each other at the top of the Empire State Building, thinking about, that as a famous meeting place in the movies. And so the point is you can win the game, but only if you have something in common with the person you're looking for, right? They have to have seen Sleepless in Seattle, or they have to know that Times Square is a famous place in Manhattan.
Mm. So that is a little bit of a problem, right? When you think about
that's right, because we don't
yeah.
know what we'll have in common with them. I mean, by assumption, they're looking for us too, if you're playing this game. But other than that, what do you have in common? What would they imagine you would look for? So the first people to propose radio SETI suggested looking at the frequency 1420 megahertz, which is the 21 centimeter line in astronomy, which at the time was the only known source of radio emission in the sky, at a narrow frequency in the sky. And it's radio waves that are produced by hydrogen, neutral hydrogen, all throughout the universe. And so it was the first emission line, we call it, in radio astronomy that was discovered. And so it was the one frequency that had some kind of salience. It's as if you went to a city and it had one tall building, right? That just screams, this is the special spot. And where else would you go except that very tall building? Now, since then, we've discovered there are many other emission lines in the sky, but that is the most prominent one. And they said, well, that's where you should look, next to that line. You should tune your radio dials to 1420 megahertz and point at nearby stars and see if anyone is transmitting.
Yeah, so the other way to think about this is also, as you say in the paper, is to look for some sort of fundamental constants.
Right.
Right, and presumably an advanced civilization will have sort of the same system. At least the fundamental constants will remain the same. But there are some arbitrary ways we actually make them, right? So there's a scaling issue with those constants, but maybe the difference or the ratios of those constants will remain the same.
Right.
Universally.
So to radio astronomers, the thing that we'll have in common with aliens is their radio telescopes. And so to them, the obvious thing to look for are things that are bright in radio telescopes. But to physicists, the things that we'll have in common are physics, because they need physics to build those telescopes and to understand that there's someone out there to find. And in physics, we do have, our favorite units, meters and kilometers and seconds, and grams and pounds and all these other units that we use. But those are very anthropocentric. There's no reason that aliens would use those. And so if we're trying to say what wavelength or frequency should we tune into, we don't want to pick a round number like, a meter or something like that, because there's no reason they would know that unit. But there are units that we have in common, and those are the so-called natural units. So Max Planck in 1900, after showing that there's a fundamental constant in nature, which we now call Planck's constant, pointed out that there were three fundamental constants that describe nature. They don't describe like the mass of things in nature. They just describe the way nature works. One of those is the strength of gravity, so Newton's gravitational constant G. One of those is the speed of light, and that's universal. And now we understand it's actually a fundamental part of space and time. It's not just this curiosity about how fast photons go. And then the third was the Planck's constant, which describes in some sense how the quantum world works and sets the boundaries between the quantum world and the classical world. So all three of those constants would have to be known to physicists throughout the universe, because they're just descriptions of the universe. And it turns out if you combine them together in ratios in the right way, you can form a fundamental unit of length that isn't arbitrary. It's not a meter. It's a unit of length that has real significance to everyone in the universe. You can also define a time, which is the time, the speed of light, and that length. You combine those and you get a time or a frequency. And you can also define a mass, or energy, the Planck energy or Planck mass. And so Planck argued in his paper in 1900 that all people, and indeed all beings, including extraterrestrial beings, would recognize these fundamental constants. He actually said that in his 1900 paper, that we have these units in common with extraterrestrials.
And so the idea here is, if you were to do some sort of communication attempt or some sort of listening attempt, maybe those fundamental constants need.
That's right. I wanted to put these two ideas together, and just explore and see whether Planck's insight that these are universal constants of nature helped us with the frequency selection problem, and helped to find a frequency that we could use. So the problem, though, is that the Planck frequency, if you combine those units, is way too fast. You can't generate light at that frequency. In fact, the frequency is so high that you have to start worrying about things like, black holes and the nature of space-time if you were to generate such a photon. It's a tricky problem. So you can't really use it in that sense. But there's another constant of nature, the charge of the electron. And it's not just the charge of the electron, it's also the unit of charge for the proton and the unit of charge for everything. And it really is fundamental to the way that quantum electrodynamics works. It's not just a description of the content of the universe, it's really fundamental. So if you combine that with Planck's constant and the speed of light, you get a constant that's quite famous in physics called the fine structure constant. And it's dimensionless. It's just this number. It's roughly 1 divided by 137. And it sets the scale of a lot of atomic physics and quantum mechanics concepts. It roughly decides how describes how electrons and photons interact. It's this important number. But it's dimensionless. It's just a small number, a little less than 1%. And no one knows how to derive it mathematically. Right. It just seems to be the way the universe is. So it's a small number, less than 1%. So if you multiply the Planck frequency by it, you get a lower, slightly more manageable frequency. Now it turns out that frequency is still way too high. But if you keep multiplying by this small number, you end up with a list of frequencies, lots of different frequencies. And they're all described by fundamental constants. So they're all frequencies that in principle anybody in the universe could agree on. In fact, if we saw a signal at exactly one of those frequencies, we'd say that is awfully suspicious, that it's this combination of physical constants and not some random frequency. And so that was the best I could do with Planck's idea, was to create this long list of frequencies, some of which are at wavelengths or frequencies where the parts of the electromagnetic spectrum where we do SETI searches. And so I suggested these are particularly interesting spots to look extra hard when scanning the skies for these kinds of signals.
Do we have something going on at SETI?
Well, like I said, modern SETI, the SETI programs that exist today in the radio and in the optical can actually search an enormous number of frequencies at once. And so I don't have to say, oh, make sure you tune your dial to this particular frequency, because they've got this huge dial and they're scanning everything all the time. But
we have a lot of extraneous.
That's right. There's a lot of radio frequency interference. And so they have to sift through a lot of human-made signals. And so my suggestion was, well, yes, you're searching all those frequencies, and that's great. But if you happen to see something at 26.158 gigahertz, and you're not really sure if it's, real or not, and you're about to throw it out, that is the Planck frequency times the fine structure constant to the 15th power. So that's a very special frequency, and maybe give it, one extra look before you throw it out.
Right. Yeah. Especially if it's
sure. But the real lesson of going through the whole exercise was discovering that there's nothing unique about this combination in these frequencies. That Planck, for instance, when he constructs the fine structure constant, he divides, or not the fine structure constant, when he constructs his units, the Planck length, the Planck frequency, and so on, he divides the constant, Planck's constant, by 2 pi. And that's just a convention that we have. We didn't have to do that. We could just use Planck's constant by itself. And that would have given a different Planck frequency, which means we would end up with a different set of frequencies to check if they don't like to divide their version of h by 2 pi. And then, why multiply by the fine structure constant? Why not divide by the base of the natural logarithm, e? There's a perfectly good dimensionless number that everybody, that should be universal. So there's another constant, or list of them. And so there are, turns out, a lot of ways to combine fundamental constants to get these frequencies. It's not unique. And so I guess it's sort of like deciding that you're in Manhattan looking for that other person and saying, well, we have to pick a famous landmark. But you're in Manhattan. There's a lot of famous landmarks. And so you have to hope you're guessing the right one. So it narrows down the problem a little bit, but it doesn't necessarily help you find what you're looking for.
Yeah, and obviously there's a timing problem. So suppose Grand Central and Times Square are guessed appropriately, but
that's right. You're gonna say, well, I'll run back and forth between them, and if they're at the, if they've got a different search pattern than you do, you're gonna miss them. That's right. But the other lesson I got from this is that it's silly to transmit at just one frequency. I mean, we search at a huge number of frequencies. If we were to transmit, we should transmit at lots of frequencies so that they don't have to do so much guessing. And so when I see these frequency combs, I'd say we should transmit it, as many of the teeth on the comb as we can. That is, as many of the frequencies on the list as makes sense.
Right. Yeah. So if they pick up all those frequencies, even if we even if we have some sort of our sort of introducing numbers into it, I would imagine the ratios and the difference between those would be more fundamental, right? So if you transmit in many, as you say,
right,
they can see the patterns, and so those patterns would be more.
It would help them figure out what scheme, right? They might say, "Oh, look, the spacing between the frequencies that are being transmitted are at what we call the fine structure constant divided by 2 pi," and I wonder why they divided by 2 pi. Right. That whole thing, yeah.
Okay. So Jason, we'll take a quick break. When we come back, we'll talk about Dyson Spheres.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back. I want to go into another one of your papers entitled Dyson Spheres, in which you review the origins and development of the idea of Dyson Spheres, their purpose, their engineering, and their detectability. This is somewhat of an old idea, right? Has been around, got a lot of press recently. You want to talk a bit about the sort of the history of how it came about?
Yeah, it was actually back when Frank Drake was doing Project Ozma, the first radio SETI search, and the very first papers on this topic were coming out. Freeman Dyson, who was one of the great physicists of the 20th century, he had his own idea that came out also in 1960. And his idea was he wanted to know basically what the extreme limit for a biosphere or a species was. Like, how much energy could it use? How big could it get? And he worked out that there was no obstacle from physics to a species essentially consuming all of the energy that came off of its star. So, life on Earth is powered by the sun. That's where we get all of our energy, either directly from the sun or from plants that photosynthesize, or, in the case of fossil fuels or something, from plants that did that a long time ago and are now underground for us to extract, with very few exceptions, like a little bit of geothermal energy, but it's all from the sun.
Yeah.
And so, life on Earth could, in principle, use as much sunlight as strikes the Earth. It turns out it doesn't use anything like that much, but that would be the extreme limit. And then you're done. You can't use any more because that's all the sunlight you have.
Right.
But of course, there's no reason you can't go out to space and collect more sunlight. We do that with our space probes all the time. They have big solar panels, and that's what they do. And so he just wanted to know, like, what's the limit? And he worked out that there is no limit except all the light coming from the star. So just like in principle, we could, cover, say, Mars and solar panels, and use all the light that strikes Mars. We could also surround the sun with solar panels and capture all of its light. And so he was just after what the ultimate limit was. And so this idea that you would surround your star with solar panels or other things, he imagined an artificial biosphere where the sphere wasn't surrounding the Earth, it was surrounding the sun at large distance. And that's what he called it, an artificial biosphere around a star. And today, we refer to that as a Dyson sphere.
Yeah. So if you were to do that, the energy budget of that structure is constant, right? So unless you go to find energy from other stars, you're sort of topped out in terms of how much energy you can get.
Yeah, that's right. That's and that was his point. That's where you'll top out. And so that's sort of a natural place to stop collecting energy is once you've collected all of it. And his insight was that, that if you did this, or even, just partially took, say only 10% of the starlight, that you'd still be able to tell that the star was there from the outside. So if we were to see such a star, we might not see the light from the star because that's being collected by the solar panels.
Right.
But the solar panels have to use that energy. You can't destroy the energy. And so the energy would have to come off, but it would come off based on the temperature of the outer surface of this sphere. And so if that was something around 300 kelvins, because that's kind of a good temperature where you have things like water and, electronics work and things like that, lots of useful materials are solid. If you do it at roughly 300 Kelvin, then you end up with all of that energy coming out in the infrared, the mid-infrared, at around 10 or 20 microns. And so if you had, Dyson argued, a telescope that could look at the whole sky and measure radiation at 10 or 20 microns, and if you saw any stars that had a lot of that emission, then that would be a very interesting candidate for one of these artificial biospheres or one of these Dyson spheres.
This assumes that, I guess it doesn't assume, but if you have nuclear fission tamed in some engineering construct, then presumably you can recreate that, right, without actually covering the sun?
No, it turns out not for very long.
Okay.
So the reason is that the sun is a wonderful nuclear reactor.
Yeah.
I mean, that's what's powering it. So all the light coming off the sun comes from an enormous fusion reactor at the center of the sun that's producing an incredible amount of energy and will keep doing so for billions of years.
Right.
So the only reason you would want to not use all that energy, which is after all just flying off into space, and like do it yourself, is if, I don't know, you need even more energy than the sun is giving off. But in that case, it's not going to last very long because after all, the sun is converting its own mass into that energy in its core, and it has a lot of mass. And so it's hard to imagine any better solution for a long-lived source of enormous amounts of energy than a star. If they didn't exist, we'd have to invent them so that we would have all that energy.
Right. And so the original idea was really covering the entire star, but then Dyson himself sort of modified it, right? And so it doesn't really have to be one structure, but could be a swarm of small things going around.
So in his original paper, he did not specify the engineering he had in mind. He just said that there'd be an artificial biosphere that would surround the star. The impression you get reading it is that he's imagining a shell. But he was also a theoretical physicist, and so to do his calculation, he assumed a shell, which is a very theoretical physicist thing to do. So it's not clear if he was serious about that or if it was simply so that he could illustrate his point. And people did complain you can't build a shell around a star, which is true. You cannot build a shell of material around a star.
Right.
It's impossible. But there's no reason you can't build a swarm of satellites around a star that altogether block out all the light of the star, or even just some of the light of the star. And so he wrote a paper in 1966 where he said, all right, well, let's think about the engineering and whether it's possible or not. And he actually worked out a whole scheme where you could disassemble planets and build stuff around the star to collect the energy. And he stopped saying, it doesn't have to, he said, it doesn't have to be a biosphere. It certainly wouldn't be a shell. It could be for any purpose, but it's possible. And that was his point. It's the limit. We should go looking for those. And if we don't see those, well, maybe we should look for something a little less extreme.
Yeah. So if it's a swarm of satellites, Jason, this is technology that even we could potentially approach, right?
Oh, I mean, we already have our own tiny little Dyson Sphere, right? We've got all these satellites out there with solar panels collecting some of the light. So, here we go. We're on our way.
But I guess you have to, if it is realistic at some engineering level, you have to be able to transmit that energy.
Well, not necessarily. Our satellites don't transmit it. They use it on the spot.
No, I meant if we were to, sort of use just to switch into a solar energy based system, and you have these things out there collecting all that energy, converting that to whatever magnetism, electricity, and then feeding it back to Earth.
Oh, you wouldn't want to do that. That's essentially building a big lens. You're collecting all the sunlight and putting it all on the Earth. And even if you've converted it to electricity, we're still going to dissipate it as heat after we use it. You'd melt the Earth if you did that. No, the idea is that you would use the energy locally, probably, or distribute it out in some way. But that makes sense. That's the way we do things. What do most humans use energy for? These days, it's getting to be computation. And when we do our computations, we do some of it on our computers, but we actually do most of it in these giant server farms and data centers and things like that. So we farm out, our energy use all over the world to do the calculations that we spend so much of our energy doing. Or, we use a lot of energy on the aluminum we use, but we don't build the aluminum in our homes. We have places that go and make the aluminum and so on.
Right. So in the original idea of the Dyson Sphere, if it were possible, it was a civilization living on the Dyson Sphere, right?
Yeah, he called it an artificial biosphere. So he was imagining that the space stations or something like that. And there's a Star Trek episode where it is a literal sphere, and they're on the inside of the sphere. They have like continents and lakes, which, if you think about it, doesn't make sense unless you've got artificial gravity, because they fall to the star. But yeah, that was what his original justification for it was. But he dropped that quickly thereafter and said it doesn't matter why they're using the energy or where they're actually living. You don't even have to have any living things. It could just be there's one little planet with some people on it, and then the Dyson Sphere itself, is all the server farms and aluminum plants and all of the other things that we use so much energy for.
And this is, again, theoretically possible around a white dwarf or even a black hole as well.
Oh, sure. You could imagine this around any of those things. Things like neutron stars and white dwarfs, they're not very bright. They don't have a lot of energy, but maybe they're interesting for other reasons. They have, very strong magnetic fields and deep gravity wells. And so, it could be that those are interesting places for other species to go and build their spheres. And black holes are especially interesting because you can play all sorts of games with space-time and entropy with a black hole. We'd have a lot of cool experiments we'd like to do with a black hole. One of the most interesting things you can do with a black hole is convert mass into energy. Right. Dropping stuff onto a black hole, on its way in, it gets extremely hot as it gets torn apart by the black hole, and it radiates a lot of energy away. And it turns out that's more efficient than hydrogen fusion. And so the most efficient way to take a lump of fuel and turn it into energy is to drop it onto a black hole. So yeah, maybe there are black holes out there with spheres around them, and they just throw asteroids on them every now and then and collect the energy. That's a pretty good way to generate energy far from a star.
Yeah, so there was some speculation that Planet 9 is a small black hole, and if that is true, we might be close
that
to
would be
free
so
energy.
great for theoretical physics. Oh my gosh, if we could do some experiments with a real black hole, we could test quantum gravity. That'd be great.
And so you looked at, sort of the engineering aspects of it. If such a thing existed, would it be even, be feasible from a practical perspective,
Right.
from a structural and a radiation perspective?
Right.
You want to talk a bit about that?
Yeah. So I mean, when Dyson published his paper, one of the immediate objections was that you could not build such a sphere, that it's unstable. And he said, yes, it's mechanically impossible. But I always got annoyed that I couldn't find anyone that just spelled it out for the rest of us why it's impossible. I mean, Freeman Dyson was just, this brilliant polymath, and so he probably works it out in his head in 10 seconds. But for the rest of it, why can't you build a sphere around the star? So there's a few reasons. So one is that it's not in orbit around the star. It has no reason to stay around the star. The Earth goes around the star because it's in orbit. But even if the sphere is spinning, the poles that aren't spinning, and they should just fall onto the star. So the sphere, maybe it tries to hold itself up mechanically. That's fine. But it doesn't have any gravitational attraction towards the star. The star pulls on all parts of the sphere, and if you do the math out with Gauss's law, you can show that the sphere and the star do not have any gravitational attraction between each other. And so the sphere has no reason to keep the star centered, and would just kind of eventually just drift over and crash into the star and destroy itself. So that's problem number one. In principle, you could try to use rockets or something to keep it in place, but now you're spending a lot of mass, and that's not going to last very long. So the next problem is that even if you could do that, the star is pulling on gravitationally on every part of the sphere. And like I said, the poles want to fall down in because they're not in orbit.
Yeah.
So what holds up the poles? Well, it's the same thing if you go to St. Louis and you stand under the arch, the famous arch in St. Louis, or any arch. Look at the very top of the arch, and that keystone at the top of the arch. It wants to fall down to Earth, but it doesn't, because the rest of the arch holds it up from the sides, because it's got this curvature to it. And that's the same thing that holds every part of the Dyson Sphere up. It's basically this gigantic arch, except there are no feet on the ground. The feet meet at the opposite side. Now, an engineer will tell you that you can't make a very tall arch, for instance, out of butter, because eventually the mass of the butter is just so heavy that it'll just squish and it'll fall apart. You need to use something that's got a little more substance to it, like stone or metal. And so that's one problem with the sphere, that there is no material strong enough that it won't just squish under the weight of this arch, because the arch is enormous. I mean, it's an it'd have to be millions of miles, hundreds of millions of miles around. So try to build an arch, a mile tall, and you see that's gonna, that's very hard. Trying to make it 100 million miles tall, and that's just too much gravity. But it turns out that's not even the one that gets you. What gets you isn't that the material will squish like butter. It's more like it'll snap like spaghetti. So if you take a stick of dry spaghetti between your pointer fingers and your two hands, and you push it, try to squish it as if it were a stick of butter. Well, dry spaghetti is pretty stiff, and so it's not going to squish, but it will bend. And if you push hard enough, it'll just snap. It'll fold itself in half and snap, and that's what it will do. It's called buckling. And the material will just form all of these little folds, and the whole thing will crumple. So there's no reason to build one, because it's impossible. If you did build it, it would immediately buckle and collapse and fall into the star.
Right. And then you also, so just the radiation effects also create some constraints, right?
Right. And so it turns out if you could build a sphere, there is one way to do it, which is not to make it really strong, but to go the other route. And make it really, really thin. So if you make material thin enough, then the very gentle pressure of light striking the material will actually push it And if it's thin enough, the force of gravity that it experiences is small enough that they'll balance. So sort of like having a kite in the wind, you can have like a sail, a solar sail that's pushed on, not by the solar wind, but by the light from the sun. And that will keep it up, similar to the way wind holds a kite up against gravity. And so if you built a sphere that thin, then the radiation could actually hold it up. But then you've made it's so thin, it's like the thinnest gold leaf that you could possibly imagine. It's that thin. And at that point, I don't know what you're using it for. It's not solar panels.
Right. And if the organism is of any substantial size, they cannot live on it.
No, that's right. I mean, this is the flimsiest, thinnest material, that you can imagine.
Right. Yeah. So in conclusion, Jason, we talked about maybe the Fermi paradox is not necessarily a paradox if you consider all the uncertainties around the parameters. We talked about why we haven't found something out there from a communication perspective. That itself is a fairly complex problem to solve. We have some thought experiments of very advanced civilizations, what they may be doing for energy. And you've been involved in this a long time, Jason. So let me ask you to speculate. Where do you come out on this? I sometimes feel that we clearly don't understand mathematically what infinity is. I'm not exactly sure if you really have a good understanding of zero. And so anything that goes in those two directions, from a probability perspective, what we cook up may not be really mathematically consistent. So where do you come out on this problem? Do we have extraterrestrials out there? Where are we missing?
My undergraduate advisor told me there's only two numbers of things in the universe: 0 and infinity. Like he said, there's not one of anything.
Yeah, that's right.
And so if there's not one of it, I mean, we're here, so the number's not 0, so it must be infinity. Is the way that reasoning goes. There must be more out there. Right. Now, they might be very rare. The number in the galaxy might be quite small. I mean, it could be 1. It could just be us. That's entirely possible. I don't know where it is. I know that I don't know enough to answer it, and it's a lot of fun to plug your numbers into the Drake equation and come up with your best guess, but the error bars on those numbers are enormous. And so Carl Sagan put it best. He said the only test of this hypothesis that's worth anything is an experimental one, and that we can't let these kinds of theoretical arguments take the place of an actual experiment to go see if we're alone or not. And so that's why I favor actually looking and not worrying too much about how many of the things there are to find. As long as it's more than one, it's worth looking for.
Right. Theory is so much more fun, though, because
it is.
You don't need much money.
And we need it. We still need it to know what to look for sure.
Excellent. Yeah, thanks so much for this, Jason. Thanks for spending time with
pleasure.
me. And good luck with this fun research.
Thank you.
Okay. Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.